Hello, everyone. Let's welcome today Professor Francisco Castro from the UCLA Anderson School of Management with us. And his topic of presentation is electric vehicle fleet and charging infrastructure planning. This is a very important problem from our country's perspective as well. There are several startups who are focusing on either the production of bikes or cars, but also focusing on the EV ecosystem, which includes the battery packs and so on and so forth. The whole planning is a big, crucial challenge for the whole EV infrastructure. So we'll be talking about some of these ideas today in this particular seminar. And just as a precursor, at IIMA Ahmedabad, we also will be running a one-day workshop on the 12th of August, which will be dedicated on EVs and the smart mobilities. So please stay tuned for that as a separate note. But let me introduce first for today's talk, Professor Francisco. He has been a faculty member at the UCLA Anderson School of Management since 2020, and he specializes in operations and design of markets, particularly focusing on the spatial and the incentive aspects. Previously, he also served as a postdoc scientist at Uber, so that really gives the inspiration behind to work on ride-hailing services. Castro's research revolves around market design, developing models that capture essential market dynamics, and utilizes rigorous theory to enhance understanding and explore new applications. His work offers practical guidelines for approaching matching, pricing, and capacity planning problems in digital marketplaces, such as ride-hailing platforms. And today's example is one of them. Castro holds a PhD in Decision Risk and Operations from Columbia University, Graduate School of Business, a MS in Mathematical Engineering from the University of Chile, and a BS in Engineering Sciences from the same institution. Without too much delay, I would give the floor, rather the Zoom, to Francisco. And we look forward to your talk, Francisco. There are a lot of excited participants here. So the floor is all yours. And all participants, if you have some questions for Professor Castro, you can also plug them in our Q&A bar. I'll keep a tab of them. And hopefully we'll also have some time towards the end to have some discussions. All over to you. Thank you so much for joining us for the seminar today.
Hi, Abhijit. Thank you so much for the kind introduction. And hello, everybody. Just a quick note, I'm giving this talk from Chile. I'm here for a conference where I did talk about this work too, and I'm also spending some time with my family. Okay, so today I'm going to talk about electric vehicle fleet and charging infrastructure planning. This is joint work with my student, Sushil Varma. He's at Georgia Tech, and his main advisor, who is Sivatesha Maguluri, also from Georgia Tech. All right, so the motivation behind this work, it's really to think about this ongoing transition that we are all experiencing, in which we are moving to from a world in which we have internal combustion engine vehicles to a world in which we are going to have electric vehicles, right? And these advances are driven, as we all know and as we all experience, by technological advancements. Batteries are more efficient now, and we have these big companies really producing at mass scale electric vehicles. Companies such as Tesla, Rivian are some of the big players, at least in the US. And we have some older, car manufacturers such as Ford, General Motors, and others that have committed resources towards producing electric vehicles. And some of the estimates that they have is that they're going to be able to mass-produce electric vehicles by the year 2030. There's also a lot of government backing for this technology. In India, there is a lot of startups also around this industry. In Europe, this is very big, and in the US, it's starting to catch up. So the US has this Inflation Reduction Act, which was enacted by the Biden administration a few years back now, that essentially put resources into many things. One of those things is renewable energies. Okay, and as part of renewable energies, we have electric vehicle technology. And so this Inflation Reduction Act is essentially given tax incentives for companies to produce batteries and for people like you and me to buy electric vehicles. There is also the government in California that has this executive order that essentially is going to ban the sales of new gasoline cars by the year 2035. So after the year 2035, if you want to buy a car in California, it has to be an electric vehicle. Okay. So lots of government backing for this technology. And there's also this fact that the preferences of consumers are changing. People are more aware of climate challenges, and they're buying this new technology, right? And part of this transition relates also to these ride-sharing companies. And as the Jit said, like I have some experience working on these companies, and I know firsthand that they're starting to think very seriously about incorporating electric vehicles in their fleets. In the US, there are a few examples. So there is this company Alto, which operates only using electric vehicles. And it operates in some of the major cities in the US, such as Los Angeles, where I live, Dallas, and others. Then there's Uber, which now if you go to the Uber app, you will see an EV option. And they are talking to Tesla to incorporate some of the Tesla vehicles in the Uber fleet. And now I've taken like several Ubers, which are not longer a Toyota. Now the Uber is a Tesla. And there is this company in New York City called Rebel that also operates only a fleet of electric vehicles. And my student, Sushil, he spent 3 months working at Tesla, and he was helping them to think about capacity planning and infrastructure planning. And essentially, that's how this project started, because Tesla has this long-term vision of having a robotaxi fleet of electric vehicles. Okay, and so they're running experiments to try to think about what the market is going to look like and what are the capacity and infrastructure planning requirements to have this business. Okay, so essentially motivated by this last part, in this talk, we're going to study a transportation system, such a ride-hailing platform that operates only with electric vehicles. Okay, and what we're going to have here is going to be a spatial setting, and we're going to have these electric vehicles, EVs, distributed in space. The vehicles are going to have different battery levels, and we're going to have charging stations also distributed in space. So we're going to have customers arriving into the system, and upon arrival, we have to match this customer to one of the cars, right? And so this is going to be a first decision that the operator has to make, which is, which EV am I going to dispatch to serve this request? Okay? And then once I choose the vehicle that I'm going to match to the request, the vehicle is going to pick up the rider, and then it's going to take the rider to his or her destination. Okay? As vehicles serve customers, their battery level, their state of charge, or SOC. So I'm going to use throughout the talk SOC for state of charge. You can think of this as the battery level of a vehicle. So as the vehicles serve customers, this is going to decay. And so eventually we're going to have to charge the vehicles. All right. And so this is the second sort of like decision that the system operator has to make, which is, when do I send a vehicle to a charger and for how long? Yeah. So that's essentially the system dynamics and the type of decisions that we're going to care about from the perspective of the system operator. I believe I have a question.
Yes. The question by Shekhar, he asked, why should system operator choose the EV charging point location, and shouldn't the customer have a choice in that?
Yeah, so very good. So first of all, here, what I'm gonna assume is that the EVs are, the charging locations are given in the system. So I encounter this system where I have certain charging locations in space, and the system operator is like Tesla or Uber, who is matching the customers to the cars. And then what I choose as a system operator is, among all the chargers that I have, which one am I going to use to charge the vehicle? Okay, assuming that I have access to that charger. Hopefully that clarifies the point. Okay? Please stop me if there are any more questions. All right.
Yeah, then none now. Yeah.
So the research question that we have here is, given an arrival rate lambda of customers to the system, so this is the trip requests that we have, and a target service level alpha, let's say we want to serve 90% of the demand, how many EVs and chargers are required to operate to achieve that performance? All right. And there are two parts to this problem, or the way we're gonna approach this question is in two parts. First, we're gonna provide a universal lower bound. Okay, so the idea here is to try to have an understanding of what's the minimum number of EVs and chargers that are required to achieve a service level alpha. And here, I'm not gonna impose any policy. The idea of this universal lower bound is really to say something fundamental about the system, something like, under any policy that you can imagine, what's the minimum number of EVs and chargers that they need to achieve alpha? The best that I can do. Okay? And why the minimum? We care about the minimum number of EVs and chargers because these are expensive assets, right? So we want to minimize these expensive assets. And the second part is, okay, now that I know the best performance, how do I achieve that best performance? And for this, I have to come up with a policy to manage this system that achieves this best performance. So those are the two parts to a problem. And here I want to stop for a second, and this is also perhaps related to the previous question. So what I want to say here is that our goal in this work is really to provide a system level understanding of capacity planning and infrastructure planning decisions, as well as insights into how to manage the system. But we are not here focused on the granular decisions, right? So really, we are going to take a macro view of the system and try to provide a capacity and infrastructure planning prescription, but I'm not going to say something about exactly how to manage the system in different kind of situations that can emerge, okay? So really, this is going to be about a macro view of the system. All right, so in terms of literature review, really quickly, so this topic is very hot these days. There are many people working on electric vehicles, people working on charging of EVs, and also people thinking about capacity and infrastructure planning. What I would say that's different, like the main difference that this work has compared to other works is that we're taking the system level view, and we're focusing. But at the same time, we're going to add the spatial dimension to the problem in the sense that we're going to model the pickup times, we're going to model the drive to a charger times, and at the same time, we're going to make this decision of number of EVs and number of chargers, both at the same time. There are other works that think about number of EVs, number of chargers in a sequential way. In this paper, we're going to do that. We're going to make that decision at the same time in an asymptotic regime. All right. So those are some of the main differences with previous work. And something I want to highlight here, I was talking about this with Devjit before the talk, is that there is a nice connection between what we do and queuing theory. Okay? And so before I take that question, let me just go over this one slide. So in management science or operations management, there is this classical problem of capacity planning. Okay? So the typical problem there is that, let's say you have a call center with n servers, So n people answering the phone, and you want to figure out, okay, how many people do I need to provide a good quality of service? All right. And what people have found is this square root safety staffing rule that essentially says that the number of servers n that you need is equal to lambda times t. Think about lambda times t as the average number of people in service. So this is the arrival rate lambda times the time that it takes to serve a customer. So you need at least that, obviously, but there is an extra buffer term that is of the order of square root of lambda. Okay, and that buffer term is there to absorb random shocks. And if you set the number of servers like this, people have shown that you provide a good quality of service. Okay, so that's in a system without spatial components. It's a classic system in operations management. And now, if you add the spatial component to the problem, so now if you think of a system without electric vehicles, but a system in which servers need to pick up a customer before the service can start, then the capacity planning prescription changes. So you need at least lambda times t. This now becomes the number of customers that are on trip going from point A to point B, customers that are in a car, plus a second order term that is of the order of lambda to a 2/3, which is there because of the pickup times. Okay, so what you see here is that this second order term for a system with for a spatial system is fundamentally larger than the second order term for a call center. The difference comes from the pickup times. Now in a spatial system, there is more workload in the system because we need to get to the customer before we can start service. And because of this additional workload, we need fundamentally more vehicles to provide a good quality of service. Now, in a system with electric vehicles, which is what we care about in this talk, we think that there is a fundamental difference compared to a spatial system without electric vehicles. So a few differences here are, first, that we have a non-negligible amount of time that we're gonna be charging an electric vehicle. That's one. And second, here we need to drive to a charger, which is going to impose a trade-off between the number of chargers that we have and the fleet size. Okay, and this trade-off is going to become more and more clear throughout the talk. So this is going to warrant new ideas. Here in an EV system, we have a very large state space. So we not only have the spatial component, but we also have this dimension of the state of charge of the vehicles, and we have many vehicles. So that's a lot to keep track of. And so we need to think carefully about how we can, like, despite of having this large state space, how we can keep track of things here and how we can say something about this complex system. The dispatching decisions that we need to make are going to have to be cognizant of the state of charge as well as the location of the EVs. And so there's going to be a trade-off here that we're going to see later in the talk between state of charge and pickup distances. And we also need to design a good charging policy. Okay, so those are some of the main differences. And so we really, there's a need here to provide some understanding of what are the capacity and infrastructure planning implications in this new type of spatial system with electric vehicles. And I'm sorry it took a long time to explain this slide, but now I can take the question.
The question was more about the application of EV in the future. So I think it's a more general question, Francisco.
Let me see.
And the second question now, which is, other parameters that can be given for planning, like commercial viability, utilization, real-time availability, and so on and so forth. So it's more of a comment and not really a question. So we can move ahead.
Okay. I'll happy to stay to linger after the talk and talk to anybody who wants to discuss things further. All right. So let me give you an overview of the results. So this so this slide is going to look a little bit technical, but I'm going to try to parse it and to provide as much insights as I can. So first, the two main results of this paper are first that we provide this universal lower bound for the number of vehicles and charges that you need to achieve certain service level alpha. And we have a matching upper bound for that lower bound. Okay, so that comes with a policy essentially to achieve the best performance. And our capacity planning prescription now take this form here, where really I want us to focus on the first sort of like equation here that has some interesting aspects that are not present in a system without electric vehicles. So the first thing to note here is that for the number of vehicles n, what we're going to need is something that is 1 plus r times some expression here, where r is the ratio between the discharge and the charge rate. Okay, and so what this is essentially saying is that this first order term, this r was not present in a system without EVs, but now in a system with EVs is present. And so this first order term is fundamentally larger compared to a system without electric vehicles. So we need a lot more vehicles. Because we need to charge vehicles, we're going to need more vehicles in a system with EVs. And this sort of tries to put a number or an expression or a way to think about how many more vehicles we're going to need. But what happens is that the second order term here, which before was lambda to the 2/3, now can be smaller. Now can be as low as lambda to the 1/2, right? 2/3, it's larger than 1/2. So now we can reduce the second order term. Okay. And we're going to see where that gain is coming from. So overall, we need more vehicles up front because we need to charge vehicles. But the additional vehicles that we need in order to deal with spatial effects are going to be less because this is what this expression is saying. It can be as low as 1 lambda to the 1/2. Okay, and I'm going to provide more insights into why this is the case. This result also characterizes the trade-off between fleet size and number of chargers as parameterized by this parameter gamma here. And essentially what we'll see is that if we have a larger gamma, essentially a larger gamma here translates into a larger number of chargers, which translates into a lower fleet size requirement. Okay, so this is characterizing this natural trade-off. If you have more chargers in the system, it sort of makes sense that you're going to need less vehicles. Okay, so this provides a sharp characterization of that trade-off. And we're going to propose a policy to manage this system that we're going to call power of the vehicles dispatch, which is going to provide the best optimal performance for our problem. And I'm going to describe that policy in a few slides. Okay, so any questions now?
There's one question, Francisco. He's asking, like, please elaborate how the average trip time affects the N.
Yeah, so I didn't speak about this, but this TR here is the average trip time, right? So essentially, so alpha is the service level, lambda is the arrival rate. And so alpha times lambda is essentially the effective arrival rate times TR, that gives you the number of customers that are in the system on trip, that are inside a car traveling from A to B. And so you have 1 times that, you need at least that many vehicles. And you have to multiply also, you have to add R times that, because for every mile that you drive, you need to charge, you're going to lose some battery, right? And you're going to have to charge for that, right? And that's going to take some time. And that essentially means that you're going to have at any given time a fraction of cars that are going to be charging. And that is that second term here, that R times alpha lambda TR. Okay, so that's essentially how the average trip time is entering the equation, both in the sense that you have cars that are driving at any given time, and also because the cars lose battery across time, some of them are going to have to be charging. So in that sense, the TR enters the equation for the number of vehicles. Okay? I think this also might become clearer and clearer in a few slides. I think I have more questions.
Yeah, there's a few more questions. One is that how is the discharge modeled? And could this framework be used for fleet with swappable batteries?
Yeah, okay. So for the discharge, essentially, in this model, we're going to have a charge rate and a discharge rate. And just for simplicity, I'm going to assume that those are constant. So if a car is at a charging station, it's going to charge at some rate RC. If a car is driving anywhere, the car is going to lose battery at rate RD, discharge rate. And also, we are going to assume that those are constant, but I think you might be able to incorporate, at least in the simulations that we have, incorporate non-constant rates. Okay, and then for swappable batteries, that's something that we are still exploring. Like, we still don't know how we would incorporate that in this model. So I will defer that for another time. But that's something that we are looking into these days. Thank you for the question. Okay, so let me describe the model give you a little bit more details about the model. So we're going to have N EVs and M chargers, and they will be distributed in a bounded region, as in the picture here. And we're going to consider a fluid system. What do I mean by a fluid system? Essentially, think about a deterministic system. There is no stochasticity in this system. Later in the talk, I'm going to do a simulation, and the simulation is going to have a lot of stochasticity, and it's going to be very close to or closer to reality. But just for the sake of tractability, I'm going to assume that the system is deterministic. Customers are going to arrive at a rate lambda. So note here that the arrival rate of customers in this model is constant across time, which is not the case in reality. And at the end of the talk, I'm going to tell you what happens when you assume that the arrival rate is not constant, and you have an arrival rate pattern that is more like it's high in the morning, then it goes down, and then it's high again in the afternoon. Okay, most of our results are going to go through in that case with some small caveats. Okay, but for simplicity, I'm going to assume that the arrival rate is constant, and also to understand sort of like this is the base case, right? So if we want to understand something more complex, first we want to understand the base case. Okay, so that's why we are focusing on this constant arrival rate. The spatial dimension plus the SOC dimension are going to result in involved dynamics, and so essentially here is sort of like a key modeling technique in this work, which is that because it's going to be really hard to keep track of where the cars are in the system, if I want to estimate pickup times, which is TP here, and I want to estimate the drive to a charger time, which is TC, that's going to be really complicated if I have to keep track of all the cars. So what we can do is to use certain approximations that have been given in the literature. So that approximation is this expression here, which essentially says that the pickup time at any given time, the average pickup time, is going to be larger than some constant divided by 1 over the square root of the number of idle EVs. Okay, what does this mean? Essentially, this comes from the following idea. If you have one point in space and you have k other points around it, you can show that as k becomes larger and larger, the distance from the closest k point, one of these k points, to this one central point, scales as 1 over square root of k. Okay? And so for any policy pi, the pickup time has to be larger than some constant or times the minimum distance, the scaling of the minimum distance. Okay, and you can do a similar approximation for the chargers. Okay, so we're going to assume those bounds. So for any policy pi, the pickup time has to be larger than this lower bound, and the drive to charger time has to be larger than this bound. And this is actually, it might look like a naive modeling technique, but if you look at the data, when I was at Uber, I look at the data to see if these kind of like approximations work well or not, and you get surprising results where you see that actually this 1 over a square root of the number of idle cars is a very good approximation for the pickup times. Okay. Okay, so with that, so that's one part of the model. Now I want to provide an idea of how the system's dynamics are going to evolve, or how we're going to capture that. And so for that, I need to define this lambda e pi of t, which is the effective arrival rate of customers into a system. Okay. And with this, what I can say is I can provide a generic set of differential equations that are valid for any policy. And here I'm just going to give you a sample of this set of differential equations. If you want to look at all the equations that describe the evolution of the system, I invite you to take a look at the paper. But so for the first equation, essentially, the idea is that Q here is the number of customers in the system. And so what this equation is saying is that the rate at which the number of customers in the system changes is equal to the effective arrival rate of customers minus the rate at which customers depart. The rate at which customers depart is simply the ratio between the number of customers divided by the time that the customers spend in the system, which is the trip time plus the pickup time. And that you can think of Little's law. If you know Little's law, this is essentially that. And so the difference of these rates is going to control how the rate of change of customers in the system is going to evolve. Right? So you can write another equation for the SOC. So S here is the state of charge, the aggregate state of charge of the system. So if I take all the vehicles and I add up their state of charge, the rate at which S changes is going to be equal to the rate at which cars are charging. So CC is the number of cars that are charging at any given time. RC is the charge rate. So CC times RC is the charge rate, minus the discharge rate, which is this expression here, which is essentially the vehicles that are not charging and that are not idle. So these are the vehicles that are driving, essentially, times the discharge rate RD. Okay, so that's gonna essentially that's gonna tell me how the aggregate SOC of the system evolves, the difference between these two rates. And there is another equation for how the number of vehicles that are charging changes over time. Okay, and it follows the same idea. So essentially, all the equations that we're going to use to describe the evolution of the system are going to be of the form input rate minus output rate. Okay, but what's interesting is that really I can write this system of equations that describe the evolution of the system for any policy pi. And really, in the paper, I only have 2 or 3 more equations, but just this very reduced system of equations is enough to provide ideas of infrastructure and capacity planning requirements of the system. Okay, so I don't have to describe the dynamics in detail, but I just need to look at some part of the dynamics, and that's enough for me to have an idea of capacity planning requirements. Okay. So now I'm going to show them the first main result. And so maybe this is a good point to stop and see if there are any questions.
There are a few in terms of, one is that, are we assuming that the fleet consists of same type and size of batteries?
Same time?
Same type and size of battery. Are the batteries?
Yeah. Very, very good question. Yeah, so yeah, that's correct. So I'm assuming that all vehicles have the same battery pack size. I'm assuming that all chargers have, so you can think of this model as I'm taking for all the cars the average pack size of a fleet. I'm taking for all the chargers the average level of charge. So you can have level 1, level 2, level 3, and whatnot for charging stations, but I'm taking here the average performance of those chargers and the average performance of those battery pack size. So the whole model here is like an average model. Yeah, so that's what we're doing here. And the simulator that we built, though, and we'll be happy to share the simulator, can take in like anything that you may want to model, such as different battery pack sizes, different charging stations, different locations, charging stations with different number of charging posts, and it can become, it's a very rich simulator. So I'll be happy to share that with anyone that's interested. But for the model, we're taking a simple approach to have some understanding of this system. Yeah.
And there's another question whether on the discharge modeling, the question is that how is the discharge process modeled? Is it proportional to distance or modeled as a nonlinear function or something?
No, yeah, good question. It's modeled as proportional. It's modeled as proportional.
Right, and there are a few more questions which are more qualitative. We can take them maybe at the end, Francisco.
Okay. Yeah, thank you. Okay, so this is the first main result of the paper that essentially says that give me any policy that you can use to manage the system. So here for policy, I mean something very general, a matching policy, a charging policy, a routing policy, any policy, right? So however you want to manage the system, then if I look at the effective service level for that policy, the effective service level is simply the ratio of the long run effective arrival rate divided by the exogenous arrival rate. If I want that, I want that the effective service level is larger than alpha, then what I need is that the minimum number of vehicles and the number of chargers, they have to be at least these expressions that are here. So N and M have these lower bounds. And this is within our model, this is true for any policy. Yeah. And so just to give you an idea of what's going on behind these expressions, it's actually very simple. And so I'll try to convey the main point here. Hopefully it doesn't get too complicated. So if you think about the average time an EV spends driving to serve a customer, it spends some time on trip, going from A to B. It spends some time picking up a customer, and there is some other time, which is the drive to charger time. Okay, so for every customer, I'm gonna spend some time doing one of these actions, right? Now, alpha times lambda is essentially the rate at which we serve customers. So alpha, lambda times TR are the customers that are driving, that are in a car, as we said before. And if I multiply that by R, it's gonna give me the number of customers that are, the number of cars that are gonna be charging, okay? And so now what I can do here is essentially replace. So what that means is that at least I need R alpha TR lambda chargers in the system, okay? Because those are going to be the number of vehicles that are going to be charging at any given time. So I need at least that many chargers, but I need a little extra more because I need to have extra chargers so that vehicles can actually, when they finish a trip, they go to a charger that is free, and that free charger hopefully is not too far. It cannot be too far, otherwise I'm going to spend too much time driving to a charger. And so if I parameterize that extra number of chargers by lambda to a 2 gamma, and I replace that here, what I get is lambda to a minus gamma. And so I'm trying to approximate now the time that a customer, that an EV spends driving because of serving a customer. And so for the driving to the charger time, I get this approximation. Now, the key idea here is that I have a lot of vehicles that are charging. How many vehicles I have charging? I have at least this many here, right? R alpha TR lambda. And I can use those vehicles that are at charging station to serve new customers. And so if I do that, the number of cars that are essentially available for pickup are of the order lambda, because I have order lambda vehicles charging. So I can use them to serve new customer requests. And so now I get another approximation for this term here, which is of the order 1 over square root of lambda. And so now I get this nice approximation for the time that an EV spends driving due to a customer. And if I multiply this by 1 plus R times alpha lambda, so alpha lambda are the customers that I have to serve, right? And I also need to multiply by R times alpha lambda because I have to compensate for the charging. So if I multiply my time here by this rate, I get the number of vehicles that I need. And that's essentially this expression here becomes this lower bound that I have over here for the fleet size requirement. Okay, so it's very intuitive. It's just keeping track of the right rates and keeping track of the time that it takes to serve a customer. Okay, but the main and sort of like the main insight here is this part here, that really, because you have to have cars charging at any given time, you can use those cars to pick up customers, and that enables you to reduce pickup times by a lot, which reduces the fleet size requirement as measured by the second order term, this lambda to the 1 minus lambda. Okay, so that's the lower bound, and so this is like a, an ideal performance. So how do we achieve this ideal performance? I have to start thinking about what's a good dispatching policy, and to think about a good dispatching policy, I need to think about trade-offs. What are the main trade-offs in this system? Okay, so let's say we have a customer arriving to the system. We need to decide what EV we have to dispatch for pickup. So there are two things. So one, we want to match the customer to the closest EV or a very close EV, because that's going to reduce pickup times. And that's something that we would like to do, right? At the same time, we want to match the customer to an EV with high enough state of charge, so that we don't deplete the state of charge of the system too quickly, right? So you have this tension here, and so the first question is, okay, you have this tension, but is it really important? Is it really a fundamental tension? For example, can we ignore the SOC and just match to the closest vehicle? And what we find is that no, you cannot do that. Actually, if you try to use this policy, that always matches to a closest vehicle, then you're going to end up with a fleet size requirement that is much larger than the fleet size requirement that we came up with in the previous slide. Okay, so the bottom line here is really that this closest dispatch policy is not going to be good enough in this system where you have this additional dimension of the SOC, right? And so we need a policy that thinks about this trade-off between pickup time and a state of charge in the system. Yeah. And so we propose a power of D dispatch policy that overcomes this trade-off. And here's the policy. This is how it works. So we're going to ignore the vehicles that are driving with customers or driving to chargers. We're going to say those are not available for us. And so we're going to consider the D closest vehicles. Instead of considering just the closest vehicle, we expand that to be the D closest vehicles. And among these D closest vehicles, we're going to pick the one with the highest state of charge. Right? So if you have 10 vehicles that are the closest, just select among of them the one that has the highest SOC. And that's the policy that we propose. And what we find is that if you manage this system using this dispatch policy, you can actually achieve the lower bound performance, or almost achieve the lower bound performance. Okay, so in the lower bound, gamma was able to go from 1/3 to 1/2. All right. So the larger the gamma, by the way, the lower the number of vehicles that we need. And so before, gamma was able to go all the way to 1/2 in the lower bound. Under this policy, we can show that it can almost be 1/2, except for a term that is of 1 over NT, where NT is the number of trips that you can do with a full battery. And so as NT increases, really this bound or this performance becomes very, very close to the lower bound, the optimal performance. Yes. Okay. So we are nearly achieving the lower bound performance. The bottom line here, the takeaway of this slide, is this power of D policy, right? It's able to achieve this optimal ideal performance as given by our lower bound result. And it sort of resolves this trade-off, right? So you don't want to match two vehicles that are too far, because that's going to give you maybe that's going to give you a high SOC, which is good for the SOC of the system, but pickup times are going to be too far. You don't want to match two vehicles that are too close, because maybe those vehicles have a low SOC. And so to navigate this trade-off, you can choose the right optimal D, and when you optimize over D, you get this good performance. Okay, so we have a policy here that performs well. That's the main message here. Okay, so I'm gonna. Okay, so the results essentially that we provide tells you what's achievable and what's not achievable in terms of these scalings. So here in the horizontal axis, I have the number of chargers. As you move right, you have more chargers. Vertical axis, I have the number of vehicles. As you move upwards, you have more vehicles. And what we show is that this blue region here can be achieved by some policies, right? But especially the boundary can be achieved by our power of D policy. And what we see is that as you increase the NT, which is the number of trips that you can do with a full battery, so as the batteries become better and better, you can achieve more and more of this region, right? But there is a minimum, there is a limit to what's achievable, okay? In terms of vehicles, you can never go below to 1/2 here, so you can never be let's say 1/4. So this number here, 1 minus gamma for the number of vehicles can never be below 1/2. Okay, and that's essentially given by because of the pickup times. The pickup times are limiting how far we can go down this vertical axis. And for the chargers, we have a minimum requirement of 2/3. We can never go below than 2/3. So this 2 gamma here for the number of chargers can never be below 2/3. So, and that comes essentially from the spatial considerations of the system. You have to have enough chargers so the drive to charger time is not too large. Okay, so the bottom line is that there are limitations. We have to operate at least with certain number of vehicles and certain number of chargers. Okay, we can never go below certain thresholds. And then there is this diagonal line here that characterizes the Pareto frontier, and it characterizes the trade-off between number of chargers and number of vehicles. Okay, so we have this nice characterization of what is achievable in terms of number of vehicles and number of chargers, as given by these scalings. And a last comment here is that we're so there is a fundamental difference between this EV system and a system without EVs. So here we have the square root of lambda. So the second order term can be a lot smaller compared to the lambda to 2/3 scaling, which was the case in the system without EVs. And so there is a very different sort of like capacity planning prescription when you start thinking about all the physics and the dynamics of an EV system compared to a system without EVs. I'm not going to talk about the proof idea because I don't have time for that. So I have a few slides about simulations, but before I go there, I think this might be a good point for some questions, if there are any.
Yeah, there are a few questions. One, they asked if you're modeling the charging time.
Yes, I'm modeling the charging time. That's essentially a choice of the system operator. I didn't talk about the policy, the charging policy in detail, but there are a few policies that you may consider that sort of make the results that we have valid. So one simple charging policy is once the vehicle finishes a trip, you send it immediately to a charger and you leave the vehicle charging until you need to use the vehicle, until the vehicle reaches full battery, or until you have to use the vehicle to serve a new request. Okay? That is going to work, but you can see how that can be inefficient if vehicles are constantly going to charging stations. So another policy that is going to work in this setting is a policy where you have, where you say, hey, send the vehicle to a charger and leave it there until it reaches certain percentage of charge of battery. That let's say 50%. After the vehicle has 50% battery, the vehicle is good to start serving new trip requests. That type of policy will also serve. Okay? Although the performance of our results degrade a little bit, but we are able to capture that as well. Yeah.
Sure.
Any other questions?
There's one more question on, is estimated trip distance accounted for in the policy? For example, if it is a short trip, you can service it with a vehicle with a lower SOC.
Good. Yes. So in this analysis, we are not capturing that type of sort of like trade-off that emerges. But if you wait for a few slides, I'm going to talk about a policy that sort of accounts for that in some ways, and we'll see what's the performance in that case. Okay?
And the final question is that, can distance travel be matched with the high SOC cars dispatched for pickup? So I think you mentioned about the two trade-offs. I think this links to the first statement of the trade-off, whether can we match the high SOC cars based on the distance. Yeah.
So it's similar to previous.
Similar to previous one, yeah.
Yeah, good. Those are very good questions, and maybe I'll put a pin on them and talk about them in 2 slides or 3 slides.
Sure.
Okay. Okay. My student actually, he built this big simulator that doesn't have any simplifying assumptions in terms of we consider the average trip time. No, here we have a spatial setting, trip requests arrive, and they have some origin, some destination that's random. Okay, so every trip request it's different. So the length of the trip is going to be different. The arrival rate is some random arrival rate, and what else? Yeah, and essentially in this spatial setting we have a fixed number of chargers that we're going to change, but they're fixed in the sense that the location of the number of chargers is of the location of the charging station is fixed, and the vehicles are going to move around the system. Okay. Okay, so that's essentially the setting. If you want to learn more about the specific of the parameters that we use to run the simulator, all of the details are in the paper. I invite you to take a look at them. But now I'm just going to talk more about the results from the simulation rather than the specific parameters that we use. Okay? So the first thing that we do here is try to validate our average, in a way, our average results in this more stochastic random system closer to reality. And so what we do is we set a given beta. That beta is going to set essentially the number of chargers, M. And so the betas that we consider are 1, 0.9, 0.8, 0.7. And for different arrival rates, I'm plotting here the second order term, the lambda to the beta. Okay? Just for you to see how that is going to increase as we increase the arrival rate. Given the number of chargers and given the service level alpha, in which is set to 90%, we want to achieve 90% service level in this simulation, we find the fleet size N. Okay, and so we find the fleet size N that achieves this 90% service level, and then we essentially calculate the difference between N and 1 plus R TR alpha lambda, and then we try to fit this lambda to the 1 minus gamma. And what we find is we find certain numbers for 1 minus gamma. The point is that this empirical exponent that we find in the simulation matches very well the exponent that we have in the theory, right? So even though here there is a lot more noise, the dynamics are more complex, right? The average system that we use to understand, the average model that we use to understand this system, it's very close to the simulated model. And so that's the point of this. Yeah, so that's one thing. Another thing that we observe in the simulation is that, so on the left here, I'm showing you the average pickup time. And what we see is that as we change, so these different curves essentially translate into different fleet sizes and different number of charges. And what we see is that the pickup times are roughly independent of the number of chargers. However, the average drive to a charger time changes substantially with the number of chargers, which is also in line with our theory. If you remember, I had this expression that was TR plus 1 over square root of lambda. That 1 over square root of lambda was the pickup time, and it doesn't change with the number of chargers. So that's what we see here. And the third term was lambda to the minus gamma. That gamma is the number of chargers, and you can see that it changes substantially here. So the drag to a charger time changes with gamma, but the average pickup time doesn't, which is in line with our theory as well. These plots are interesting in the sense that, so here I'm showing you service level percentage. Those are the level curves. On the horizontal axis, I have the fleet size. On the vertical axis, I have the number of chargers. And what we observe here is that as we increase the number of chargers for a given service level, let's say 90%, which or 80%, which should be this level curve here. As we increase the number of chargers, we observe that the fleet size requirement starts decreasing, right? So we start moving left across this curve. Excuse me. But we see that this has some kind of like an asymptote there, which essentially means that more chargers are going to help in terms of service, in terms of fleet size requirement, but up to a point. Okay? And then on the right, I have a similar plot, but on the vertical axis, I have the battery pack size. And what this is showing is that for a given service level, as I increase the battery pack size, the fleet size requirement decreases. But even if you have a vehicle with a very good battery pack size, right, you still are going to need a minimum number of vehicles for the system to work. And so this plot is also capturing that, which is all of these results are in line with our theoretical analysis of the simplified model. And finally, I want to compare power of D versus other policies. I have here a plot of service level on the vertical axis. On the horizontal axis, I have D in the power of D algorithm. D equals 1, which is this point here, corresponds to the closest dispatch. Okay? And so what we see is that the closest dispatch gives you certain service level, but those service levels are outperformed consistently by power of D. And in particular, if I use D equals 2, right, that is already beating closest dispatch. Okay? And in general, power of D with D equals 2, at least in our simulations, seems to perform quite well and not too far of the optimal D that you would choose for battery pack size that are large enough. So the point of this plot is to say that power of D with D equals 2 has a good performance already. Okay, so you don't need a D too large to have good performance. Okay, I'm going to skip that. If I can have just one, maybe 2 more minutes, I think I'm out of time.
Sure.
Just to go over this, this is my last, second to last slide. So the other policy that you might be thinking about is closest available dispatch. So essentially, think about closest dispatch, you choose the closest car. If that car doesn't have enough battery, you essentially lose the request. But you may say, oh, that's not fair. Why don't we go to the next best car? Okay, the second closest that has, and we ask, does it have enough battery? If it does, we match it. Okay, and that's closest available dispatch. Okay, and what we're seeing on the left here is the performance of that policy across time. And I want to draw your attention to this black line here, which is the average SOC of the system under the closest available dispatch policy. And what we see here is that at the beginning, in this simulation, we initialize all vehicles with full battery. So at the beginning, we are able to serve most of the requests. So a lot of cars are driving with a customer at the beginning. But at some point, the battery level starts decreasing, vehicles are busy, and so we're gonna spend more time picking up customers, right? And so the orange part is the fraction of vehicles that are picking up customers. And what happens here is that under the closest available dispatch, if I have cars that are busy or with low battery level, I have to go farther to find a car that has enough battery to serve a request. Because I have to go further, the cars spend more time picking up customers, which reduces the SOC of the system. And so a new arrival, a new request I'm gonna have to go even further to find a car that has a good SOC. And so the SOC starts decaying until it reaches the minimum SOC that I allow in this system. And it stays constant after that. And so this is going to result in a low SOC in steady state, which translates into a very inefficient operation. If you have cars that have low state of charge, you're going to have to be charging them all the time. So that's very inefficient. But also the workload of served customers under this closest available dispatch is going to be much smaller compared to power of 2 or closest dispatch. What I mean by workload here is that is the ratio between the actual miles driven with a customer divided by the miles requested. Okay, so this closest available dispatch has a bias towards shorter trips, and that reduces this workload essentially. Yeah. Yeah. So bottom line, this closest available dispatch might seem a good idea, but it leads the system to a bad performance in terms of SOC and workload. So you might prefer a power of 2 or closest dispatch. And our sort of like advice, given this work, would be to just use something as simple as power of 2. Okay? I don't have time for this, so just as takeaways. So in this work, we talk about infrastructure planning. We prove a novel infrastructure planning result for EVs in the style of heavy traffic. And we characterize the trade-off between fleet size and battery packs, fleet size, battery pack size, and number of chargers. We propose a dispatching policy, power of D. In simulations, we find that power of 2 performs well. And the key sort of like managerial insight, if you want, is that you have to use the vehicles that are at charging stations. And by using them, you can dramatically improve the performance of the system in terms of fleet size requirements. And we verify our theoretical results from our simplified model in this more realistic simulation. Thank you. Yeah, sorry, I went over.
No, I think, thank you, Francisco. It was very elaborate and very useful kind of prescriptions for the practice, I would say. There are a few questions. Maybe we'll take up at least the ones which are more direct. One question was related to the, are we considering the waiting time in case of charging stations?
Okay, so I'm going to assume that the question is if there is a queue.
Yeah, are we considering the wait times at the queue? Yeah.
Right. That's a good question. So in the simulator, we do have queues at the charging stations. In the theory, we don't have queues, okay? But in the simulator, we do. And what we see in the simulation is that these queues are very, very small, and the wait times end up being very, very small. And that's because we have enough chargers. We have enough of these buffer chargers, essentially, that there is always some charger that's empty. And so we observe very small queues, which translates into very short wait times at charging stations. So it doesn't become a problem in our simulation. But if you had to wait more, that would degrade the performance a lot, actually.
Sure. But Francis, in your model, you do have wait times in the queues also, right?
In the model, I don't have wait times. I don't have queues at charging stations.
Okay.
I don't have queues at charging stations.
So what happens if there are not sufficient chargers? You lose the customers, or?
Yeah, you lose the customers essentially. So that's gonna degrade your alpha service level.
Yeah.
But that's the model, right?
Yeah.
In an ordinary practice, you wouldn't. You would put the car in a queue, right? But the point of this talk is to say, hey, you need enough chargers so that those cars are not waiting too long, because that can degrade the performance of the system.
Service level.
at least of like to think about how many more chargers do I need to avoid that type of problem. Yeah.
Beautiful. There's a question also on the relationship between the arrival rate and the pickup time. I think the question was that should it have an inverse relationship or should we reverse of what you have shown probably?
Yeah. So yeah, that's a good question. So the key idea here is that so the pickup time is inversely proportional to the number of idle vehicles, right? So if you have more idle vehicles, that's like my example of K points in space. If I have a lot of K points in space around this one point, the distance to a shortest point is going to be smaller and smaller, right? Now, in our case, those K points are idle vehicles, vehicles that I can use to match to a customer. And now the key insight I said is that you can use the vehicles that are charging, right, to pick up customers, okay? And now the vehicles that are charging are proportional to the arrival rate of customers to the system, right? So the more customers I have in the system, the more vehicles I'm going to have at charging stations. Okay? So that's where the inversely proportional relation comes from.
Sure. Another question is more, I would say, application of the model. The question is that typically projects are greenfield, which means you do not know much about the demand, you do not know much about the distribution of pickup points, anything. So in those cases, how do we use this model for planning processes when there's no data?
Yeah, that's a great question. To be honest, this model essentially, like the key one input to the model is the arrival rate of customers. So I think in general, if you don't have a good idea of the demand, what I've done in the past is to go and look at similar situations, settings that I think might be similar to start thinking about it. But another thing that you can do, I think that might be useful, is to have a lower bound demand, right? To say, okay, for my business to be profitable, I need at least this much demand, okay? And once you think about that, you can think about, okay, for this minimum demand that makes my system profitable, what's my infrastructure requirement? And then you go from there, right? And you start gathering data if you actually launch your business. I guess that's the way I would think about it. Yeah.
Very interesting. Also, surveys could help to assess the demand. So there could be other options as well. Yeah, great. Another question, is there a consideration if an EV reaches a location, drop a customer, it must have a remaining SOC, at least to take it to the nearest charging station? So I think more about the model, yeah.
Yeah, that's incorporated in the model. Yeah, definitely. We need enough SOC to go back to a charger. Otherwise, we wouldn't take the trip request in this model. Yeah.
Okay. Yeah, when the vehicle is in charge, do you always try to reach the max SOC? Not really. You also measure a partial charging, right? So
yeah, partial charging, and that's a sort of that in the model we allow the system or the vehicles to be partially charged and to be able to be available for pickups. But the key thing is that if you're managing the SOC of the system in the right way, by taking these cars that have high SOC to serve trips, you never end up in a situation, or you seldom end up in a situation where a trip with very low SOC serve trip requests. Okay, but you can also have a policy that says, hey, you have to charge this vehicle up to 50% or up to 20-30%. If the vehicle has lower battery and the vehicle is at a charging station, you cannot use it for pickups. We can analyze that case too, but the results are very similar. although the performance degrade a little bit.
Yeah, yeah. I think the other questions are more qualitative, but maybe one of them is interesting is, do you have any recommendation to how to distribute charges in the city?
Yeah, so that's an excellent question. So the way I think about this work, right, as I mentioned at the beginning of the talk, is this is a macro, like I'm stepping back, right, and I'm seeing the city from like way above and trying to understand like how many things I need. And once you have these like macro guidelines as given by these capacity and infrastructure planning prescriptions, you can start thinking about like a more granular optimization problem. My feeling is that that's going to be very related to the demand patterns that you have in the city. But I think, at least as far as I know, that seems to be an open question in terms of like guidelines or theoretical guidelines. There is some work that study, and I can point you to the references, but there is some work that study using like a more engineering approach. Like here are the demand patterns. This is my budget of chargers that I have. Where do I place them? And you can do that by solving like a big optimization problem. Yeah.
Sure, sure. Maybe we'll take one final one, is more about any recommendations, which is better, battery charging or swapping?
Yeah, so I have one data point about this, which is like I think in 2015 or 2014, there was a bunch of papers about battery swapping. And I forget the name of the company. So, but there is this one company that was working with some people from with some professors, and they were trying to optimize this battery swapping, and essentially the papers got published, but the company went bankrupt. So, so I don't know if that was because the technology was not there at that point, or just because battery swapping seems not to be a great idea. The one thing that I see against battery swapping is that it's very asset heavy, right? So you have to have this buffer number of batteries to do the swapping, and at the same time you have to have a team of people swapping the batteries, right? So that's going to be a lot more expensive, and the technology now it's there in terms of batteries, right? So batteries they have enough, the pack size is big enough to do several trips, right? And it's getting better and better every day. So there is no reason, I think, at this stage for having these additional assets and potentially that are potentially more expensive. Yeah.
Sure. Well, thank you so much, Francisco. I know you waited for quite long to answer all the questions as well. We went much beyond the time. But I think all those discussions were so helpful. I think you shared some very nice prescriptions for practice in terms of setting the infrastructure. There's always, as you said, a lot of papers in the engineering domain, which looks at more holistic optimization approach. But giving such nice, cute formulas for number of chargers, number of vehicles, the ratios, and those are kind of very interesting kind of policy prescriptions. So thank you so much for sharing your work with us today. I'm sure all the participants here, many of them are from practice. I'm sure they're excited with the outcome. So thank you again, and I hope we'll be able to host you again in the future. Thank you so much.
Thank you so much for the invitation and for everybody for the engagement and the great questions. And I do apologize if I didn't answer some of your questions. Please feel free to reach out to me. If you have further questions, I'll be happy to set up a Zoom call or just reply via email. And if you are interested in this work, the paper is available in my on my website, but it's also there is an archived version of the paper as well. So again, Devjit, thank you so much for the invitation. It was a pleasure.
Yeah, and before we end, we also planning to do a one-day workshop on electric vehicles and smart mobility on August 12th. So if some of you are here and you would like to join hybrid for some of the events, so please, I think we'll put up the registration link for some of the hybrid events. So thank you so much, Francisco, again. And thank you all the participants for joining us this evening or wherever you're joining from, and hope to see you again for the CTL seminars. Thank you.
Thank you. Bye.